Center HPC here at UIBK. My name is Thomas Fahringer. I'm the coordinator of this research center. We have been a bit silent with our lecture series for quite some time, but I thought now, with the improved technical capability of these different streaming media or communication services, we can do the whole thing virtual. And I thought it would be a great opportunity to start with Director Professor Dr. Erwin Laure from the Max Planck Computing Data Facility to start this series up again after quite some while. So it's a great honor to introduce Professor Erwin Laure to give this lecture keynote presentation as part of our lecture series. At the beginning, I would like to repeat again, I propose that during the presentation only Erwin Laure has his camera on and all others mute and turn off the camera. And then after around 40 minutes, when we start the question answer session, we can turn on the cameras, at least for those that actually want to ask some questions so that we see who that person is. And with that, a few words on the biography. So Professor Erwin Laure is the director of the Max Planck Computing Data Facility in Garching. At the same time, he's a professor at the TU Munich. And before he joined the MPG, he was a professor for high performance computing at KTH Stockholm. And at the same time, I believe the director of the biggest HPC computing center in Sweden. Probably even Scandinavia. I'm not sure, but it's pretty big compared to Austria, probably. Then he also was and is coordinating numerous HPC EU-funded projects. He participated in countless EU projects in a leading role. Just to mention a few: EGI, BRACE, CRESTA, Epigram, AllScale, BioExcel, and many more. And I should also say I'm quite proud to share some common roots with Erwin Laure. Actually, we both started our career as part of the group of Professor Zimmer at the University of Vienna, where we worked together for several years on various HPC topics, mostly related at that time to high performance Fortran. And I also should mention that Erwin spent several years as technical director of the prestigious EGE project in CERN. So his research interests include a wide spectrum of topics, including programming environments, languages, compilers, runtime systems for parallel and distributed computing, with a focus on exascale computing. So with that, I hand over to Erwin for his keynote presentation with the title Towards Exascale Computing in Europe.
Yeah, thank you very much, Thomas. Thanks for the invitation to hold this lecture here. It's really sad that we have to do this over video and I can't be with you in Innsbruck, but let's hope situation will improve and then sometime soon we can do something more in person. And yes, as Thomas said, I want to give you a little introduction on what is happening in terms of exascale computing, particularly in Europe, but I also want to tell a little bit where I see most of the challenges and what we, particularly at Max Planck and the MPCDF, are doing to tackle those challenges. So I guess most of you are familiar with this graph. This graph is from the top 500 list. That's a list that is issued twice a year and lists the 500 most performant high-performance computing system in the world. The green line on top is the aggregate of all 500, and the middle line is the top system that you see on Earth. And as you see, it's a pretty straight line. Take care, this is a logarithmic scale, so we really see the exponential growth in terms of system performance. And if you just extrapolate, then, well, we are pretty close to reach performance of 1 exaflop per second, which means really it's 10 to the 18 floating point operations per second. And indeed, the first systems are planned to be installed perhaps even this year, but certainly next year in the US. But these systems, they have numerous challenges, and that's why it's not just a matter of fact that they will appear, but there has been lots of preparation towards them. And there is a seminal study that was done in 2008 by DARPA under the coordination of Peter Kogge. And they started already in 2008 to think about how can we achieve an exascale system. And they actually thought that the first exascale system would be in place around 2020. So we're pretty close to those projections then. But of course, it's not just a technology thing. I say, okay, we can build bigger systems, so we build bigger systems. There needs to be a reason why we want to build such enormous HPC systems. And indeed, Exascale has the potential to really be a game changer and to enable new breakthroughs in many different sciences. It's really from fundamental science in the physics, astro, to climate weather is important, life sciences, we're going to talk about that a little bit, material science, but also the whole big data, artificial intelligence area has increased a lot and needs enormous resources. You can have a look at the scientific case that was issued 2 years ago by Praise, or last year even, which actually lists those projections and those potentials that exascale computing has in the various sciences. There is also a strategy paper this year or last year from the Gauss Computing Center in Germany that also shows from a domain science point of view what impact exascale can have. And in order to prepare for those large machines, so-called pre-exascale systems are being put in place. These are typically systems with several hundreds of petaflops. So still one order of magnitude below the exaflop, but really large-scale systems. So there are currently two important systems in the US, the Sierra and Summit system. They look pretty much the same. The difference is how many GPUs they have. They are by IBM and NVIDIA. I don't know whether you see my mouse pointer here, but the graph on the right lower part of the slide that shows how that system, a node of that system is actually composed. And you see it's a tremendously complex system. So you have 2 power 9 CPUs. Each of the CPUs has 3 GPUs attached to them. You have normal DRAM, you have high bandwidth memory, you have different interconnects, you have non-volatile memory. So all the technology you can think of, they have crammed into this node. In Japan, we have the Fugaku system, or as they called it before, the Post-K, that's by Fujitsu. That's an ARM system. In that sense, quite homogeneous, but also it's basically consisting of 4 chiplets, so it's also a bit difficult to use. And in China, they are building on their own technology. There is the Sunway chip of the Taihu Light system and the Dianhe 2, which is based on Intel. And some years ago, they thought that they would bet on the Knight's Corner and the Knight's Landing of Intel, which we all know was stopped by Intel. So they are now developing their own GPU, the so-called Matrix 2000. So again, this will be basically a system quite similar, or is a system quite similar to the US systems with some CPUs, but lots of GPUs that actually bring in the compute power. Why are these systems actually looking so complex? Why can't we have just scale up the systems we have? Well, the problem is that we are facing the end of Dennard scaling. Some people said we're facing the end of Moore's law, which is actually not true. Moore's law is the upper line here, the number of transistors you can cram into an area. And as you see, this is still basically holding, and we see exponential growth here. But what has stopped is Dennard scaling, which means that we could get improved performance by allowing the frequency to go up, because we were running into a power wall and the chips got basically too hot. So we still see that the single thread performance is increasing a little bit, despite we keep the frequency at the same level. But this is not something that helps you as an application programmer, because that performance increase of a single thread is basically due to the ever-increasing vector units that they put on the chip. So it's despite it's a single thread, you still have to use parallelism and you need to exploit that. But where power now really comes is basically by the amount of the logical number of cores. So essentially the multi-core and many-core systems that we all know now, and that reach from tens to actually hundreds of cores in the case of GPUs. And that basically makes life quite difficult. So we have this challenge that we have an enormous level of parallelism. If you, with the current 2 gigahertz scaling speed of a processor, you need basically on the order of 10 to the 9 floating point units to exploit, go to exascale, right? And in order to get those enormous amounts of floating point units into a system, we have quite some heterogeneity. We have CPUs, we have accelerators, GPUs, but potentially also other accelerators, other units, FPGAs, some people are experimenting with. We have vector units and so forth. We also see this quite heterogeneity in memory and storage as well. We have high bandwidth memory, non-volatile memory, solid state disk, going to object stores, changing the whole stack that we know. And we have a plethora of programming models these days. Most use MPI, we have OpenMP. When it comes to GPUs, it's a complete mess. We have CUDA, we have OpenMac, OpenMP, HIP, OneAPI. It's really, really difficult. And so reaching performance portability has always been a very difficult problem, but it's actually getting worse than making it easier. Also, when we think of exascale machines, it's not just the classical scaling and performance improvement of codes, but we really need to start to think of numerical approaches, of new ones, perhaps even new methods that are enabled by the sheer amount of computing power that you have available these days and people haven't thought about. And finally, we are more and more starting to see we're going away from single large-scale simulations, but embedding these simulations in an environment, in an integrated workflow. I've here an example from our colleagues at Jülich, where they describe how Earth system simulation actually is being done, where you have simulations, you have data analytics, you need deep learning AI, you need visualization. So you need all those components playing together to solve a scientific problem. So this is a first look at the future exascale systems that are being built in the US. Interestingly, they're all built by Cray, well, now HPE, as HPE has bought Cray last year. There is a system at Argonne, Aurora, that's based on Intel technology. So they will use the next generation of Intel CPUs, the Sapphire Rapids, plus the Intel Ponte Vecchio GPU. And then you have two quite some similar systems, but they will use different generations of chips, both on the CPU and GPU side. There is Frontier at Oak Ridge and El Capitan at Lawrence Livermore. So they are building on AMD technology, the AMD EPYC CPU and the AMD Radeon GPU. As I said before, programming models and performance portability is a problem. And you see this here already with those systems, right? The Intel is betting on what they call one API, which is, as the name says, neither an API nor one. It's really a collection of tools, but it's basically all built around data parallel C++. So that's the technology they are promoting and where they see the future. While AMD is promoting what they call HIP, which is their version of CUDA in a sense, but of course not compatible. So there is a big challenge if you need to use all of those systems, how to program them. But what is happening in Europe? Well, Europe has been quite behind for a while, but several years ago, there has been a massive movement saying, look, Europe needs to do something in order not to fall behind the US, China, and Japan. And in 2018, the Commission started a so-called joint undertaking, which is a form of funding that they can do, which is a similar thing as they have done for Airbus, for instance, where the whole budget is being put together from the EU and the member states. And as you can see on the map, essentially all of EU has by now joined this joint undertaking. And they really have two main pillars. One is they want to build large-scale HPC systems in Europe up to exascale systems. So there is the infrastructure itself and the operation thereof. But they're also doing a lot of research and development in basic technologies, in applications, but also, interestingly enough, on processor technology, trying to have digital sovereignty and have their own European processor. This is the EPI project that some of you might have heard of. And this really has the goal to develop this processor technology under European control in order to diminish Europe's dependence on US technology or Japanese technology, if you take Fujitsu or so. And they have two streams here. They want to build a general purpose processor, which will be based on ARM technology. And they're also trying to build an accelerator based on RISC-V, the open technology. And particularly with the accelerator, they also want to go beyond HPC and particularly interested to see how can they support autonomous driving, so meaning targeting AI, big data, and other markets. This endeavor is being coordinated by Bödel or Atos. And as you see in the timeline, they are planning to have first systems with the first generation of the processor already this year. We'll see whether this happens. And then towards 23, 24, the second generation of their chips. So we're all very, very curious to figure out how the chip performs at the moment. It's all still very secret and you don't get much information, but hopefully we'll see this chip appearing on the market soon and at least in some systems so that more people can actually use it. But as I said, one of the main pillars is to actually build large-scale systems in Europe. And the joint undertaking has recently acquired a number of HPC systems. So they've acquired some mid-range petascale systems in some smaller countries, but also 3 large-scale pre-exascale systems, one in Finland in CSC, one at Cineca in Italy, and one in BSC in Barcelona. Of these, the Barcelona system, I don't know whether they have signed a contract yet, so there is nothing publicly known. But both the Leonardo and the Lumi systems, they have signed the contracts, and those systems will be installed this year and next year in those places. The larger of these is Lumi. It will really be one of the fastest supercomputers in the world. Will be a Cray system with over 500 petaflops. So basically half an exaflop already. And what they do is really, they build the Swiss Army knife of the Nordics. So there will be a standard x86 partition, there will be cloud services, there will be normal storage, parallel storage, there will be accelerated storage on flash technology, there will be some specific part for data analytics, object store, and the big part will come out of a GPU partition. So this will come out of the AMD GPUs. So in a sense, quite similar to the Exascale systems that are being built in the US. The Leonardo system in Genève is a bit simpler, only 2 partitions, but also building a lot on GPUs, and they are betting on NVIDIA, so they will have almost 14,000 of the A100 GPUs in their system. And then they also have what they call a data-centric module, which is a more standard module, but with fast storage, NVM storage. So let's get back to what we said are the challenges at the Exascale, right? This is at the level of parallelism, is the heterogeneity, and you've seen some of this heterogeneity now, and the level of parallelism, how to program them, which are the programming environments, and potentially novel approaches. How can we address them in the applications and make sure that there will be a sufficient set of applications capable of using those systems when they appear? And that will be pretty soon. And one approach the European Commission has been taking is to fund what they call centers of excellence. So these are large-scale projects starting in 2015 that cover many different domains. And the goal is really to build an Exascale community, to make sure the codes are exploiting the systems well, and there can be actual science being produced on those systems. And this is a truly European endeavor. As you see, it's most European countries are part of those centers of excellence. It's over 500 institutions participating in them in one way or the other. And they cover a wide range of different disciplines, from energy, materials, climate, biomedical applications, engineering, personalized medicine, and so forth. So it's really a wide range of different application areas. And as Thomas already said, I was actually in charge of running one of the first centers of excellence that started in 2015 in the first wave, which is called BioExcel, the Center of Excellence for Biomolecular Simulations. And I'll just tell you a few things about that. And it's most of the centers of excellence, they have a similar setup, right? So on the one hand, you look at the solutions, you look at the software. It's important to have widely used software that really has an impact. Make sure you have the core developers on board, and also look, as I said before, into workflows and usability of the code. On the other hand, there is the services. You need to do training, you can do customization, consultancy, and so forth, and addressing academia and industry. What BioExcel is looking at, when you look at the whole spectrum of biological applications, you actually start at the well, actually at the quantum level, you start at a subatom level, but then you can go up to the molecule cells, organs, people, or even full populations. And the core competence of BioExcel really is on the subcellular level, so going from atoms up to a cell. And important areas here of applications is drug discovery, biomarkers, but also biomaterials and biophysics and so forth. And it's real science that is being enabled by these applications and by the work for Centers of Excellence. I just show you two examples here. One is how certain, I'm not from biochemistry, so please excuse, I have no clue what this is about, but it's a Nature paper, so this is very good. And it shows how Valium actually works with antidotes and how these interact. Or for a pharma company, actually, they did simulations to predict how drugs can be taken in via skin patches, right, rather than pills or so, and how this permeates the skin. So, is this okay? The question that you have here is most of the codes are petascale, right? So, how do you go really from the petascale performance that most of the codes have today to exascale performance? Meaning, how do you increase performance by a factor of 1,000? And clearly, this is not something that you can do by just scaling up the code itself and run a simulation 1,000 times faster. You run into the limits of strong scaling and even the limits of weak scaling and so forth. So you need to decompose the problem, and particularly in GROMEX, which is one of the leading molecular dynamic simulation programs, a part of BioExcel, you can try to improve code performance of a single simulation still. If you do this 10 times, right, by using vectorization, using GPUs, proper decomposition and so forth, it can probably be done. Then you can have ensembles, meaning multiple simulations in one single simulation job. So you can probably have another factor of 10 here. And then you can have large workflows running many jobs. So if you have, 3 times a factor of 10, which is probably doable, you can reach this scaling factor of 1,000, while you will probably not be able to reach it with a single simulation. So you need to do the classical and computer science divide and conquer approaches. And this is what is done here. These are some recent results running on the current the PuTTY system in CSC, scaling up to 512 nodes, meaning more than 5,000 GPUs by combining all them. Right, doing efficient SIMD parallelization, doing the main composition over CPUs and GPUs with OpenMP, CUDA, having multiple so-called walkers, which are the simulation going along the trajectories, so having the ensemble inside the job, and that allows to reduce the time to solution from almost 200 hours to 6 hours, which is a major improvement. Now, let me also tell you a little bit what we are doing at Max Planck. So this is our computer hall in Garching. And what we do at the MPCDF, we run the central Max Planck supercomputers, which are, when you look at the pyramid of supercomputers, you have at the bottom university systems or departmental computing systems, and then you have on the top, you have the major European national supercomputers, like this is the SuperMUC at LRZ. You have the system at CSCS in Switzerland, for instance, which is the largest in Europe. And we run the large-scale supercomputers that kind of bridge the gap, that are in between. And our systems are open for all researchers of the Max Planck Society. We also have a partner center, which is mentioned here as a DKRZ. Das Deutsche Klimarechenzentrum in Hamburg. DKRZ is a domain-specific one dealing with climate and weather research. So those are our current main systems. We have a system since 2018 with 12 petaflops peak performance, some 130,000 Intel cores, and some older GPUs. And we are currently upgrading the new system, which is called Raven, which will be based on Ice Lake processors. They are starting to ship those processors next week to us. And that will be a system of integrated 20 petaflops, where 15 petaflops comes from a GPU partition. So we will have almost 770 A100 GPUs, the latest NVIDIA GPU generation. And that makes it one of the largest European GPU resources for academia. But as I said before, building those systems in a sense is easy, but having software to run efficiently on them, that's the difficult part. And we are having a large HPC code development group, which makes contributions to many important codes being used in the Max Planck Society. You see it's ranging from materials, bioscience, plasma, biophysics, bioinformatics. Overall, we are having 15 HPC systems and 3 large AI projects that we are running at the moment. And we cover the whole spectrum from code optimization to method development, but also more down-to-earth software engineering, making sure that the code is modularized and can be maintained in the long run. And the challenges we're covering, well, is what I said before, right? This is what people are seeing. GPUs, extreme concurrency, heterogeneity, memory hierarchy, impact of AI. And we are trying to tackle them really by employing the whole tool set that is available to us. Of course, the core tools are MPI and OpenMP. But even there, you need to look into a modern version like shared memory of MPI-3, asynchronous MPI. CUDA awareness is very important when you go to GPUs. SIMD is important. Using the GPUs, task parallelism. We are experimenting with performance portability frameworks, AI frameworks. Mixed precision is something that has come up recently, and also fault tolerance. Let me just give you some examples of what we could achieve. So this is the gene code, which is one of the most important codes in plasma physics, so simulating the tokamak reactors. And that has been ported to GPUs. And as you see here, this is a weak scaling, a very good weak scaling. The lower pass are the GPUs, up to 512 nodes, over 3,000 GPUs. And you see a speed up of 10 to 15 compared to the CPU only, which is a very good achievement for a GPU code, right? Typically, you see a speed up of 3 to 4. So this was a very good result, and you see very good scalability. But also sometimes you see less good scalability, like this is Octopus, which is quantum dynamics materials code. And so when you increase the number of nodes, the speed up, well, you see a good speed up, but it's widening, right, towards the ideal. So this is going up to 8 GPUs here and then 16 GPUs. If instead you put the GPUs on a machine, right, like you put 8 GPUs on a node, you can get much better performance. So again, this is where the world is going, right? So currently we still have those systems with 1 CPU and 2 GPUs, but probably we have soon those nodes with 8 GPUs or even more. So that's an important thing to look into. We're also doing task parallelism. That's an example of protein sequence alignment. And that's actually quite interesting because this is a code that is challenging BLAS, the current standard tool for sequence alignment, and we are getting actually better performance, I think, than BLAS, or at least are on par. And by going to HPC, we can really enable tree-of-life scale alignments now in hours, which was months. So you see excellent performance up to 512. I need to say, as you see here, those lower parts are extrapolated from subsets of the simulation because you need actually 512 nodes to get the whole amount of data into the system. One of our flagships is ELPA. That's an eigenvalue library that is being used in all major compute centers and for many of the major material science applications. And it shows excellent scaling up to 40K cores on our systems, but of course, it's quite dependent on the matrix size, right? Clearly, when you have a small matrix, then you can't use this large amount of cores. A key part of all that is SIMD vectorization, as I've already said before. We do by default, we do the compiler guided auto vectorization, basically the SIMD directives. But that is very often not really detecting all the potential you have for SIMD. So you need to go to do explicit vectorization with SIMD intrinsics, which we do for performance critical kernels. But that's a tedious task and it's very architecture and compiler dependent. And so we have developed a library that is now being maintained by INRIA in Strasbourg, which basically provides intrinsics as templates. So it's a C++ abstraction layer with basic data types, operations, and reductions. And it's currently supporting all major CPUs that have vectorization, including the Aurora chip of NEC, which is essentially a new vector system. So we're very happy if you tried it out, and perhaps that can be useful to you. We're also experimenting with performance portability frameworks. You probably have heard of Cocos and Raja. Those are two frameworks developed in the US, and they are in the core of the US Exascale software projects. And we found them mature enough to be used, so they do work. However, there is, compared to a native CUDA or OpenAC version, you see here different GPUs, there is still quite a performance penalty that you have to pay. So we are currently now working together with the developers of Cocos to see how this performance penalty can be reduced. But you know, it's an interesting path that you can take. Another important thing you need to look at is the memory demand of some applications. Like here, it's again a plasma code, which is a 6D code. And when you have 6D and you need to communicate, you're having extremely large halos, meaning the area of data that is being owned by other processors and that you need to get in or out to the other processors. So you need very large machines because you have a very high memory demand and very high communication demand. So you need to have pipelining schemes and have asynchronous communication to actually mask the communication that you have, so you can get quite good weak scaling, as you see in here. Now this is of course the textbook thingy that you say, oh, use asynchronous communication. But if you just use normal MPI implementations and you use asynchronous, quite often you don't see much speed up. These are the blue bars here that we found out with Intel MPI. And we actually analyzed that together with Intel. And the reason is that, well, you do your asynchronous MPI, you launch your call, the system knows that you want to do some communication, but then it doesn't do it. So what Intel has done, they have a progress thread that they pin to one of the cores that actually push the MPI implementation to actually do the transfer. And that is the orange bar here. That allows a much better speed up than we had before. And a final example that I want to show you, which is a kind of new thing, is going into mixed precision. So by default, codes are using double precision. This is basically the standard, and people are not thinking much about that. But if you can go to lower precision, you can actually get a much better performance out. You can double the performance of vector units. Well, if you go from double to single precision, if you go to even lower precision, you can get even more out of that. And the same is true also for GPUs, right? GPUs have typically a double performance in single precision than they have in double precision. And as another side effect, you're also reducing the amount of data that needs to be communicated. So we looked at Gene again. This is this plasma code that I already mentioned. And the initial experiments, as you see them here, they show a very good numerical results, even with single precision. And by doing that, we can overall have the code improvement by 35% faster. And some parts are actually almost only half of the time they need. But like with every optimization technique, there is always a big depends. We're also using the mixed precision in the ELPA library, right? The eigensolver that we have. And we tried them for the diagonalization in the Picard type iterations. And you see here that the number of these steps, the SCF steps, and in the early steps, you can tolerate lower performance. You see that the single precision is this dotted line, and you have good conformance with double precision. But then after a number of iterations, like, 7 here, maybe 8 here, depending on the matrix size again, you see a degradation, and your numerical results are not good anymore. So it's a good tool, but you need to be very careful where you use that tool. Just a final example, we're using also AI frameworks. We worked on parallel training over several GPUs, and we have good scalability up to 100 GPUs. So I've been talking almost only about computing here, right, and CPUs and GPUs, but as I said in the beginning, also the memory and I/O subsystem is changing quite significantly and becoming a problem. And we are starting later this year in April a new project under the Zero HPC scheme that's called Admire. It's being coordinated by Jesus Carretero from Madrid, and quite a number of German partners here as well. And here we look at really the whole memory storage stack, from backend file systems to data locality awareness, job scheduling, scheduling of I/O, co-scheduling, HPC and data-intensive applications, also doing in situ optimizations, meaning that instead of spitting all the data out and doing post-mortem analysis, you try to do analysis already in situ, and thus reducing the load on the I/O system, storage virtualization, in-memory storage. So lots of different techniques that we want to try out here, and I'm looking forward to that, and perhaps I can tell you in a couple of months a little bit more about that project. So just to sum up, we have a great future ahead, and we will see seeing the exascale systems coming up very soon, but it will be complex. So we have to deal with more complex hardware, different CPUs, accelerators, memory hierarchies. We have more complex application workflows. We see, I haven't shown that, but it's a trend that you try to combine simulation with artificial intelligence. We need to handle extremely large data sets. We need to deal with sensitive data, perhaps. So we need to have efforts on all levels. We need to build the systems. The application support is very important. And then eventually, of course, also the data solutions that we need to put in place. Yeah, with that, I would like to thank you very much. And are there any questions?
Well, first of all, thank you very much for your excellent presentation. I hope everyone can hear me now. I turned on the audio. So your presentation was not limited to Europe. You actually also covered some of the largest supercomputers that are there or will be ready in the USA, China, and Japan in the near future. Basically, you started from the EPI, from the processor development here in Europe, to system programming, programming APIs, all the way to domain-specific applications. And that's excellent because I just looked through the audience. We have something like 50 participants. Many of the names I know: computer scientists, domain scientists, numerical mathematicians, not limited to Innsbruck, some of them even coming from Vienna, Linz, and so it's fantastic. There should be a lot of interesting questions. Hopefully we can get a good discussion going. And I would like to start maybe with a quick question, because I know you worked on so many areas in HPC, and you pointed out that some of these fastest computers in the world are heterogeneous. So what's your take on programming these systems? Is it a simple answer, well, everything is domain specific, it depends on the application, or is there something you would propose, let's say, to domain scientists that have a potential for these kind of supercomputers that are there or that will reach exascale very soon? What's your take on how to program these systems?
So I think we need to differentiate here at least 3 levels, and this is shared memory, distributed memory, and GPUs, right? And I think when it comes to shared memory and distributed memory, then the answer is quite clear. For shared memory, use OpenMP. It's mature and it's basically commonly used. When it comes to distributed memory, again, there has been lots of discussions whether MPI is really the tool taking us forward towards the exascale, and several people have been quite skeptical about that. But I think today also there is no real question anymore that MPI is the way to go. Also, I think you have to think about that. You will, on an exascale systems, you will most likely not have 10 to the 9 MPI racks, right? But you have, as you see on the current systems already, quite fat nodes with lots of capabilities and very performant, up to the hundreds of teraflops. Perhaps soon we will see even nodes that have a petascale performance. So we are really talking about thousands, tens of thousands of MPI racks that you need to use. And this is something that people do without any problems today. Where it's still an open question is how to use GPUs efficiently. And here is, unfortunately, we see this battle of the developers, of the vendors, the battle between AMD that is promoting their HIP. NVIDIA tries to bind you to CUDA. Intel is promoting data parallel C++. The hope is that eventually OpenMP, where lots of efforts go today, will actually help and be as performant as CUDA. So that's perhaps the way to go if you want to have portability. At the moment, you still have a little bit of performance hit, but we hope that we'll overcome this soon.
Okay, thank you. Now the floor is open. Please, whoever wants to pose a question, just unmute, maybe even activate your camera. If you cannot use audio, use the public chat. There should be a lot of questions because I see so many interesting people from all over Austria. So not yet. Then I ask my next question. So you mentioned CUDA quite a few times, right? We know there's OpenCL, which kind of fading out, but what was interesting, you never mentioned SYCL, which is kind of the next competitor. It's an open system, right? CUDA is kind of, it's more like proprietary from NVIDIA, but SYCL is the next competitor on the horizon, which has a strong impact on one API. What's your opinion on it? And do you see some real domain scientists that are interested, that want to pick it up?
Well, that's the data parallel C++, right, that I was mentioned, where Intel is betting on. It's very interesting, but it's early. So I've seen people experimenting with it, and it has a large potential. But with all the new developments, time will show whether it flies.
Okay.
But if you go, for instance, to AMD systems, like the Fujitsu one, they use OpenMP. That's it. So again, portability, it remains to be open.
So, Alexander, I see your camera is on.
Yes, I have a question concerning your remark on variable precision. You said that nowadays this variable precision becomes a very interesting option. So I have to say, already 30 years ago, this also was the question whether it makes sense to switch sometimes between single and double precision, but finally double precision won. And as you said, everybody did everything in double precision. Nobody thought about it. Now even half precision is available. And my question is GPU in particular very advantage for this half precision or single precision?
GPU is essentially a vector machine as well, right? And you typically get when you get double the performance when you halve the precision. So yes, if you can go lower precision on a GPU, you get much more performance out of that. That's what all the data analytics deep learning frameworks actually.
I know it was from this direction. You also mentioned that you were developing some software for computing eigenvalues of matrices.
Oh yes.
So is there single precision or half precision also an issue, or is this still everything done in double precision?
It's the version, the public version. It's all double precision, and I can change the slides here. Where am I? So here on this slide, we've done some experiments with mixed precision, right? And you need to be very careful, right? And in which space you're still getting good numerical results, and then after a number of iterations, basically it diverges, and you need to swap to double precision because otherwise it doesn't work anymore. So you need to be careful. It's a very powerful tool, but it can also do a lot of harm. So you need to make sure that the numerics are still okay. Yeah.
Okay. Thank you very much.
Thank you. Are there other questions or comments from the audience?
Well, maybe I can ask a question, Thomas. So I was very surprised in some sense about your comment that OpenMP will be used to program GPUs, because at the moment I don't see any move in that direction. And I mean, I talked also with some people at Lawrence Livermore, and basically what they tell me is that AMD is now preparing CUDA, where you basically replace all of the CUDA by HIP, and then you should run your code. So, I mean, I was wondering if you have any more comments about this, because to me it seems that the war is over and CUDA has won, basically.
I would not bet on that, yeah. Again, I think it depends a lot how portable you want to be. If you go to Fugaku, forget about CUDA, right? Or HIP or any like these. You need to use OpenMP. I think there is still quite some movement on OpenMP and make this the tool. If you look what Intel is doing on their GPU, we mentioned this already, SQL data parallel C++. But I asked them, okay, this is great, but we have many Fortran legacy applications. What we do with them? Yeah, and they say, oh yeah, OpenMP. So I would not say the war is over. I think the war is still going on, and unfortunately, we don't know who will win.
Okay, next question. Out of curiosity, how many of your so-called real-world domain science codes are still developed in Fortran versus C or C++? Can you give like a half or percentage? How many people are still working with Fortran?
It's a very good question, and I should have prepared myself. I can't answer it, unfortunately. I don't know, but
okay,
I'll get this to you later.
Because like 2 or 3 years ago, I asked someone from Jülich, and they told me, well, like 10 years ago, it was like 20% C and 80% Fortran. And now I think it's at least half of them is C and C++, at least.
Certainly C++ is rising, right? But I can't give you a good number, but I'll get this to you. I need to ask.
Okay, now there's something in the chat. Can you see that as well?
Yeah. So EU chips, RISC-V, as well as ARM. Why not also use RISC-V for general purpose processor rather than just using accelerators? I'm not part of this project, so this is pure speculation. But I think one of the goals they had was to really have something running in the 24 timeframe. And I think with RISC-V, there is might be a longer way to go to have a general purpose processor. So they have basically the secure path with ARM so that they have something that can be used. And by using RISC-V as an accelerator, they want to explore this technology, and if it wins, then they will certainly continue and go there. So I tell you an anecdote. I asked Jesus Lavata from BSc, who is one of the key persons also in this RISC-V development. And he said, well, they are taking the Gaudi approach. So you know that the main piece of Gaudi, who was this famous architect in Barcelona, is the Sagrada Familia. And it was very clear when he started to build the Sagrada Familia that this would last for several decades, and he will not be able to see the finished Sagrada Familia. And they're still continuing to work on it. Yeah. So he could have built basically the bottom layer of the church, and which would have been not very telling, but he chose a different approach, and he was finishing one of the portals, right? And if you go to Barcelona, you see the original portal by Gaudi, which is a marvelous piece of art. So he basically finished one small piece saying, oh, this is the potential we have with this church. Let's continue building it. And Exascale said the same approach they're doing with RISC-V, right? So they want to have small, focused effort going for the accelerator, showing the potential of this technology, and then hopefully rolling it out wider, rather than having a basically mediocre processor which has a failure to not be continued because it would take too long.
Okay. Thanks a lot. Okay, next question in the chat.
Do you see parallelization completely up in the compiler, with programmers only describing the concurrency and data dependencies, not caring of the underlying architecture? Well, yes, we've been, and Thomas and I, we started basically from that, right, with the parallelizing compilers in the 90s. I'm not a big believer in that. I know Intel has been contemplating again with particularly data flow approaches, which would do this kind of automatic parallelization, right, where you describe the data flow and the data dependencies, and then the system will take care of parallelization. And for some time, they actually thought that this could be a technology to go for the Exascale machine for the Aurora, but they also stopped that and went for the more traditional approach with CPUs and GPUs. So it's a great area of research for practical impact in a wide range of problems. I don't see this coming any time soon.
Okay. Then while we wait maybe for another question, I have one which is a bit more visionary. So I remember like 10 years ago, shortly before petaflop computer were appearing, there were the first workshops at that time that were looking into how to build an exaflop supercomputer. Is there already some events, some people looking into how to target zetaflop? Because it's a similar phase, right? Are you aware of anything? And if so, can you sketch some ideas what they believe should be done?
Unfortunately, I haven't followed any of these, but I know that there have been some presentations out there talking about zetaflops. And certainly, if you talk to Jack Dogara, he will probably be already on this. The question is whether this is realistic with the current technology. Yeah. So we are really running into with current technologies into lots of problems, most of them being energy. Yeah. If you need to use 30 to 40 megawatt to power up such a machine, that the energy bill is killing you, right? And then going another factor of 1,000. I'm not sure current technology will actually work there. So I think rather than talking zetaflop, I think it will be more interesting to talk quantum computing, to talk neuromorphic computing, to talk cryo computing. These technologies perhaps will have more potential rather than trying to even further scale current technology. I don't think we'll go much further.
Thank you very much. So the audience is getting quieter and quieter. Okay, Philip has a question. Can you speak up, unmute?
Hi, can you hear me?
Yep.
Yes. Okay, hi. Thanks for the talk. So you've talked about which programming models users of these future systems should use, and you recommended OpenMP and MPI. But my question is, how realistic do you think is it that novel programs are actually being written and run on these exascale systems compared to using the domain-specific solutions like GROMACS that exist for various domains? So maybe I'm putting you on the spot again with a percentage estimate, but in your experience, what do you think, how many research is actually being done using custom-tailored software written by smaller research groups versus using these industry standards or domain standards?
Well, GROMACS is being developed by research groups, right? So I would not say it's an industry standard.
No, but it's okay.
Most of the no, but I think your question was how many codes you will see written up from scratch or more legacy codes that you evolve, right? And I think the majority, of course, is legacy codes. Because there you have a community already that is using it, that is developing it. Developing a code that runs the Exascale from scratch is very, very difficult. But even with those legacy codes, there is lots of development. As you mentioned, GROMACS is a great example. What was it? They said 7-8 years ago, GROMACS was 95% Fortran. And it was a very difficult decision what to do. And they decided to move to C++. So basically, they have re-implemented GROMACS in C++. And this is happening in other codes as well. So there is a lot of movement in changing those codes. And even if it's a legacy code, there are lots of changes and parts or even the whole codes are being rewritten. So there is a potential to use more modern technology, even in legacy codes.
Okay, so sounds promising. Thank you.
Okay, so it's very silent now. There's still the opportunity to ask some questions. So I think at this point, I would like to thank you very much, Erwin, for your excellent presentation that really covered a lot of different aspects in supercomputers, both from your center in Europe and the whole world. You moved closer from Stockholm now to Munich. So I think there is better opportunities to collaborate with you. And I mean, you are from Austria originally, of course. Between Innsbruck and Munich, that's almost like we can meet for lunch. There is also the Austrian HPC initiative that meets once a year, I would say at least. Maybe that's an opportunity for you at some point to attend, just to increase this potential for cooperation. On the other hand, talking about cooperation, now ask Philipp Gschwandner, can you pop up the eScience webpage? We do collaborate yes. Actually. So there is the IEEE eScience conference that will be held and organized this year in September, between September 20 and 23 here in Innsbruck. We are still hoping that it will be at least a hybrid event, so that some of us or all of us can meet physically and the others can join virtually. And this is organized by Erwin Laure, who is the program chair, and myself, I'm the general chair. So it's a very visible international conference that is around for 17 years. And it would be fantastic if many of the audience maybe can submit the paper or propose a workshop or a tutorial and participate. And, you know, there will be a lot of international presenters here, people from all over the world, and it would be great if as many Austrian participants join as well, come together and have a great event for the eScience, which is very much domain science specific. There's also a lot of numerical math. This is not a computer science conference. This targets primarily the domain scientists that work on the fastest supercomputers in the world. Erwin, do you want to say a few words about this?
I would really like to invite you to provide contributions to it, either a paper or even just a talk. We are very open, and it's as Thomas said, it's a very broad conference, right? So we are looking really into broad concepts which can range from new programming models to new numerics to different approaches to certain problems. The important thing is it needs to be applied. So we want to see real impact in science that is being enabled through the technology. And if you don't want to write a paper or you're coming more from a domain where eScience, which is still a kind of more computer science application, is not really as important as your domain-specific conferences or journals. We are also accepting abstracts. So you can submit a short abstract if you have something interesting to tell, and you can then attend the conference and perhaps be part of the program. So I think what is the deadline? In April, early April, I think we have the deadline for submission. So please consider submitting. Prof, Thomas and I, we're looking forward to having a great program here.
Thank you very much. And with that, thanks again, Erwin, for being with us. Thanks to all of the people from all over Austria. I'm really totally happy that we had so many people that joined this presentation. Please stay healthy and have a wonderful afternoon. Thank you very much.
Thank you very much. Bye-bye.
Thanks, bye.
Danke, Erwin.
Gerne.
Wir haben das aufgezeichnet, würden das gerne als Video auf der Webseite für das Forschungszentrum HPC